here for this size, this the radius A of the hole, and sometimes I might use R. I still fixing this one, so either R or A. So keep that in mind. So that is the starting point. This is the first step to try to guess a good area stress function for our problem. So we start from this homogeneous one, and then from there we get such a pattern like this one. Okay. So here we come to the rigorous generations, the kind of the process. So this is the fourth order differential equations in the polar corner system, and we can plug in to solve for P1, P2 like this one. Okay. Each of the equations solution is pretty much there. The solution process is available from, for example, if you go to the library, and there's a textbook title called the Engineering Mathematics. Okay, there's quite a few in such book, and there they should have this one should be the standard the problem there. Okay. But on the other side, in my handout, I provided you a copy that kind of solution process I've written in the handout in the appendix. So assuming we know how to solve for this one, assuming the solution is there, so the first question to solve for this one, basically that is forming this one, okay? And again, for forming this one, this kind of solution is we expect the solution form should be V1 equal to some kind of form, the R to the M, okay? Something like this one, we introduce this one there and we solve for M, and then we compare and something like, just something like this one, okay? So basically here this is the solution, and for V1 we have 4 terms, okay? And here the features is this is a constant, and sorry. So the feature of the 4 terms basically composed of a constant and in linear combination of the natural log R squared, and the R squared with this one. And before we move on, then you should tell. We know that for every stress function, and this function will be related to stress. Okay. And for, okay, I can make that one later. I just want to tell you is for our physical quantities, when R approaching to infinity, for example, if we consider a huge plate, the R is so big. When R is so big, at that remote site, the distribution of the stress is still finite. So that means any terms, when R approaching to infinity, those terms, for example, this one, when R approaching to infinity, this term is going to lead to infinity. So for that case, similar to this kind of thinking, B1 must be equal to 0 to make that physically practical. Okay, something this keep in mind. But we leave that later on. Right now, talk about this one is too early. So that is the V1. And the second V2, we have a little bit different because if you remember, how do we solve for V2? The V2 is this one here. Hopefully you see. V2 is starting from here. Okay, hopefully you see this one. Okay. So V2 is regarding this one, and then so basically they have a little bit expression. I mean, in terms of coefficients, like this one. In the similar solution process, and we can find the V2 that is in such a form here. Okay. So once we have that's the psi 1, psi 2 being come up with, so that is a total stress function. That is a total area stress functions. Total area stress function expressed in the polar corner system for the particular problem here. So once we found this one, then we accomplished the first milestone. Okay, this always is the hardest part, and guess a good area function, and then go through the fourth order differential equation to solve for the general solution. This is always the hard part. And once this one been done, then remaining will be very straightforward. Okay, so this one, in my opinion, that is the disadvantage of using the area stretch function approach in two-dimensional problems, because you always have to base on very good understanding of the physical problem to help yourself to come up with a good guess. Not always the guess is hard. Okay, it's not trivial. Okay, so now we start from our second portions, and we're going to proceed calculating the stress in terms of those formulas. Again, those one corresponding is the second order differential in the polar coordinate systems. So keep those in mind, then we proceed to this one here. So by plugging to that equations, then we have such expressions here. Okay, then very long writing, and I simply take advantage, copy and paste, and then right away I do the calculation here. That is what I did from the very beginning. Once I have a pattern, I do all the calculation on computers, and that can be easily make copy and paste, and then arrange, move the terms very easily. Okay, and that's an experience shared with you. So now, again, come to here, and that is to the point. If we consider our plate is very large, and we know at our large, and then the stress at the boundary there, so this is our problems here. So for example, the hole is here. Okay, and here that is our boundaries, and sigma applied at, for example, r approaching to infinity. So assuming we consider very extreme situations like this, oops. Okay, so for stress to be finite, in particular in the remote site, then we can see for those terms will make things blow up, like this one. When r approaching infinity, this term will contribute to infinity, so this term must be gone. That means we're asking d1 must be equal to 0, right? In a similar way, this term d1 equal to 0, and then also d2. Okay, this term here, when r approaching to infinity, this term will come to the infinity, so d2 must be 0. So that is applying the physical constraint. So from here, in total 8 unknowns, we knock down 2, so remaining we have 6. Okay, we have 6 remain. So we continue. Okay. So once we have such general form, then we apply the boundary conditions. So here we come to the still in the second portion, we try to apply the boundary conditions. The boundary conditions is this. The first one, like this one here, the boundary conditions applied at here. The boundary conditions, one, applied at the remote site, so that means at the r approaching to infinity, that means at the remote site. And there we know the stress described in xy coordinate is sigma 0, 0. And right now for our stress, we describe is in polar coordinate systems. So we need to convert. How to convert? If you remember, how to say this one. So here, let me take a small element here, okay? So small element here, and we can apply our transformation of the stress using two-dimensional, for example, Moore circle, or using formula. Let me remind you what we are doing there before. This is our xy, and I pick a small stress element like this, okay? In the handout, I directly apply cosys. I directly apply the three-dimensional stress problem, but that is very generic. You can compare to this one here. Around here, we have the stress like this, Okay, and that's it, and no other stress components. And for here, we try to convert it into here rotation theta. Okay, so this is our tangential radial direction, and this is our tangential directions. We'll try to convert to here. So let me put into this one here. Okay, and how to convert? This is our ER. Sorry, this is our sigma R. Sigma R. And this will be sigma theta. And then corresponding here will be tau R theta, something like this, right? How can we do this one here? For example, we can use Mohr circle. We draw the Mohr circle for this case. In the x-plane, we have the stress is sigma and zero stress here. This is our x-plane. In y-plane, there's a nothing here, so this is our Mohr circle, right? And the center is per this drawing is like this. We want to rotate by theta. That means in the Mohr circle, we want to rotate by how much? By 2 theta. X, according to such rotation, move to x prime. Are you able to, by simply look at this geometry, to figure out the coordinates of x prime? You should. Okay, for example, you can utilize this triangle. This is sigma r. This is sigma tau r theta. Sigma r simply is given by this, right? What is this? This one equal to this portion, sigma over 2 plus this portion, that is radius times cosine 2 theta. Hopefully I'm doing right. Oh yeah. Okay. So that is the one we kind of showing here. Okay. And the same way, hopefully Ben, are you able to see it? And then tau r theta basically is this one. And that one, if you look at this one, the radius is sigma over 2. Radius multiplied with sine 2 theta. So that one, tau r theta equal to radius and times sine 2 theta. Something like this. Okay, and y here I have a minus. I'm going to double check. I will double check with this minus and leave it. Okay. But anyhow, let us take this minus continue because all the lecture content is based on this one. And okay, assuming everything there. So right now, for our boundary conditions at the remote site, we convert into the R and theta. So from the previous expressions, and again, I copy these stress like this one. Then we introduce R approaching to limit. We approaching R to infinity. Then put everything, and then you can see when R approaching to infinity, those terms will be gone. So basically leaving the C1, C2 here alone. So from here we can solve for C1, C2, something like this one. Okay, so that's the first step, boundary condition 1. The second boundary conditions happened. Let me move on to the next slide. The second boundary conditions happened here. So that is a plate. And this is a hole. Let me enlarge. Right now we move our attention to around the hole there. So here is kind of the breaking lines for the plate. Okay, the second condition, the second boundary conditions happened here. So I highlight that happened at the surface of the hole. Okay, the second boundary conditions is happened at, for example, this is the R and this is theta. That happened at R equal to A and theta equal to from 0 to 2 pi. That including all the points surrounding the surface there. Okay. And from there we can come up with is this. From here you can see inside our problem statement, we have not applied anything inside the wall here, right? So free surface without any externally applied loading. What means the free surface? Free surface, that means there's no stress, right? Okay, so basically for the second boundary conditions, we're expecting there's no stress. So let me list the two numbers here, okay? And again, here I copied the general solution of the stress of the two. Like here, we still have those kind of unknown constant to solve. And the first one is this. You see, we asking the second boundary conditions is valid for all the points on the boundary. That means for all these possible theta in this domain. That requirement is this. For this term associated with theta, for all the possible theta value, the two terms must be 0. So that means the whole thing must satisfy this one. So basically we can ask the coefficients associated with theta, simply put them equal to 0. So that means the stress will be equal to this term only. Okay, something like this one. Okay. So we require the coefficients associated with theta equal to 0 to meet the requirement for all the possible theta. So that means the very natural requirement. And then under these situations, the tau or theta is just become 0. Then for this term become 0, we're asking the remaining this one equal to 0. So that is equal to this term here. So in total, 3 equations that allow us to solve for the 3 terms, so B1, A2, B2. To this point, we completely solve those unknowns. Okay, so basically the two boundary conditions like this one. And in this slide, we have, this is the total solution. This is the complete, I would say, the solution based upon the boundary condition here. And here let us plot. For example, when theta equal to 90 degrees, so that means we're looking for is at this point here and at this point here, okay? For 90 or minus 90 degrees, and then the distributions of the two components, and for sigma theta, for tangent for this component is like here. Okay, again, this is the distribution of the stress at this point and as a function of R, okay? And then at this one, that is sigma R here, and that is, this one is component here. And again, here they're taking the radius as function of radius of R. This graph showing is the distribution of the stress at here and at here. Okay, simply we look at the different location, which means we fix a specific value of theta, and then we draw the distribution as a function of R. That is the meaning of this graph. Okay. So again, to this point, that basically marks the end of this topic. But furthermore, we can ask ourselves. For example, in terms of the design problems, I want to know where is the maximum normal stress. Okay, or I can ask what is the orientations of the principal stresses based upon this, or what is the orientation corresponding to the maximum strain stress. Another example. And another related question is this, that is addressed in the problem of the handout is this. If we consider a plate in X dimension and Y dimension that both are very huge in X and Y dimension are very huge, And here is our defect here, still the radius equal to A. Okay. Under that situation, again, we are still taking the sigma in x directions. At this moment, for example, if I impose, say, another uniaxial, another uniform tensions in y directions, say, let me call it sigma. What would be the distribution of the stress corresponding to this problem? Do you know how to solve for it? And what are the strategies for solving this? You look at this one. Here, up to now, everything is in linear combination. So that means the superposition principle should be able to apply. So you can make assumptions, say, assuming the interactions of the stress from so the problem can be decomposed into such a way, and assuming the interactions of the stresses around there can be decoupled. Okay, can be decoupled, we can make a good assumption like this. Okay, so that means you simply just repeat, and this solution has been provided there, and for this one, you simply convert, translate xy to 90 degrees, or whatever changing the corresponding, then you can get a solution to this one pretty easily and superpose together. And even for certain problem, say like this, you can still do it, right? Okay, for this case, for sign conventions, keep it in mind, for sign convention, that is negative, right? Okay, so. And I think this one pretty much cover the basic fundamental problems, and then this one marks the end of this chapter.